Walk too far. I'm just going to quickly go over one topic from the last class that I got a few questions about, which is how is the estimation of the derivatives for the filter a convolution? So again, this was how the filter applied to the input. And you can see that any element of the filter basically scans the entire input, so it contributes to the computation of every output element. Guys, can you come up front, please? So just track the 1, 2 element of this filter. That's the one that is being pointed to. It's being pointed to over here. This, when the 1, 2 element is at this location, look at where it is sitting, right? So when the 1, 2 element is at this location, it composes the first, or helps compose the first element of the output. Over here, it helps compose the second element. Over here, it's the third, fourth, fifth, sixth, seventh, eighth, ninth, right? So if you look at this figure, these are the 9 elements that it accessed, and the arrow shows which element of the output, that specific element of the input, combined with the 1, 2 element of the filter, right? So you see what I'm talking about? So this element over here multiplied W12 and it contributed to Z00. This element over here multiplied 1, 2 and helped compose Z01 and so on. So when you actually compute this derivative term over here, you're going to be multiplying the derivative with respect to this element, this input, to get the contribution of this change, right? Similarly, you're going to be multiplying the derivative of this element with this input to get the contribution of this change. So if you want to compute the derivative of W12, then these are the pairs that get multiplied. So it's going to be the derivative here with this element, the derivative here with this element, and so on, and then you're summing the whole lot up. So that is like saying I'm taking the derivative map and placing it on the input. And where am I placing it? I'm placing it with the 0, 0 element at the 1, 2 location, right? And that's giving me the derivative with respect to W12. You see how that's happening, right? And so using the same logic, if I were to compute the derivative for W00, here this element multiplies with W00 to give you Z00, right? This element multiplies with 01 element multiplies W00 to give you Z01. So going backwards, you'll be placing the derivative map starting at the 0, 0 location to compute the entire inner product, right? So basically, then if you look at it, I'll show you mine, right? So if you look at it this way, you're saying that what we find is that in order to compute the derivative with respect to any specific element of the rate, you're placing this derivative map starting at that location and then taking the inner product. Confused? Did I lose you? And so which is why for each position, you're going to be placing the filter, the derivative map at that location and computing an inner product. And you can scan left to right, top to bottom, and you get the entire weight. The derivatives for the entire weight, which is, that's the, so this is what you'll be doing to compute the derivatives. Right. And now we have some polls that, any questions? No? Okay. So let me go on with today's lecture. I'm assuming that my TAs are not going to be here. I have 4 of them who are supposed to be here and none of them have arrived. So which means our polls are probably not going to happen. I'm just hoping that one of them is responsible enough to get up and bring their remark within the next 5 minutes. Let me start. So we're going to be talking all about more about computing derivatives, and then we're going to look at some success stories. The story so far: shift invariant pattern classification tasks such as does this picture contain a cat, or does this recording include a hello, are performed by scanning for the target pattern using CDCNNs or TDNNs. These are shared parameter models that can be trained using background. And so to train it, you're going to have to compute the divergences of the output with respect to the target output for a bunch of training instances. You compute the average divergence, to the average of the derivatives of these divergence with respect to parameters, and then update your parameters using gradient descent. So for any particular instance, we'd have to pass it through the network.
Sorry, let me see your microphone for a second. Sorry.
Oh, I think I might have turned it on.
Yeah, or it's in the wrong place. It's not going to the room.
No, I think I turned it on.
Make sure it's the right one.
All right.
Yep.
So, all right. So those who are not here lost those 5 minutes of explanation about the weights. Good for them. Now, so we saw how we can compute the derivatives going back. There are derivatives for two kinds of layers. The first are the convolutional layers. The next is the pooling layers. For the convolutional layers, we saw we needed to compute derivatives going back from the output of the previous layer through the convolution to the output of the, from the output of any layer through the convolution to the output of the previous layer, and also with respect to the weights itself. And so there were two steps over here. First, we wanted to compute the derivatives of these affine maps, given the derivatives, the derivative of the divergences with respect to the activations. And that was obtained using just the simple chain rule, element wise. And then we also wanted to see, and for this one, to compute the derivative with respect to the elements of the channels of the previous layer. For any specific channel, we picked all the corresponding channels of all of the filters. And then we transposed those filters. And then the transposed filters convolved with the zero padded output maps, or the output derivative maps, in order to compute the derivative map for that corresponding input channel. So this too we saw in the last class. And we saw a corresponding version just now of how computing the derivatives for the filter too was just a convolution, except in this case, in order to compute the derivative for the filter that computed any specific output channel, all you had to do was to take the derivative map for that output channel and convolve all the input channels to get the corresponding derivatives, right? By the way, can one of you get on Piazza and tell my PAs that I'm mad at them? If they are not here within the next 10 minutes, they're all fired. My words, okay? Or at least the ones who are responsible to be here are fired. I don't need to see them again for the rest of the semester. Now, so we've got both of these. We've got how to compute the derivatives here and the derivatives for the filter. The other thing we saw was how to compute derivatives for pooling. Now, to compute the derivatives, if you were performing, oh my God, what's happened to the color? So if you were performing max pooling, the max was actually picking the largest element in any window. And so when you wanted to, and you were scanning the input like so, just picking the max within each window. So when you wanted to compute the derivatives for any specific window that was used to compute a particular output, you just pick the derivative at the output and copied it or added it to the derivative at the location from which the max was obtained. For the rest of them, there are no contributions because they do not contribute to the final output. So we saw this pseudocode for it as well, right? Now, for mean, again, we saw that within any window, you were actually computing the mean of all of the elements in the window going forward. So if you are doing when you go backwards, the derivative that was computed for the output is distributed uniformly over all of the elements that were averaged to compute that element. And so this too we have pseudocode for. Now, again, one special thing about mean pooling. Mean pooling is just a regular convolution, except that it's channel-wise convolution. In your standard convolution, when in order to compute the output at any location, You were convolving all of the input channels and adding them up, right? When you're performing pooling, you're just, in order to compute a specific map, you would just be performing the convolution with a uniform filter, a filter of uniform values over one channel to get the output of get the mean pooled output for the same channel. So the mean pooling is basically an instance of convolution. You can actually use the same convolution code, a simplified version of it to compute derivatives. Skip what's on the slide. But anyway, we've gone through all of these terms. There was one pole. Just check if the pole is alive. I'm not sure that it is. Is it not? Okay. My apologies. So anyway. All right. Does anybody want to answer the first question? There will be no polls today. Does anybody want to answer the first question? True. Second one? True, right? So both of them are true. Fine. Now, so we also saw something about resampling layers. Upsampling and downsampling layers can increase or decrease the size of the map. Upsampling followed by convolution can be viewed as convolution with a fractional stride. Convolution followed by downsampling can be viewed as convolution with a stride greater than 1. Yeah.
The fractional stride like 0.33 would give you like an upsampling of 3.
Exactly. Right. That's what they call it. Okay. It's about anyway. Convolution followed by downsampling can be viewed as a convolution with a stride greater than 1. How do we backpropagate through upsampling and downsampling layers? We didn't actually see this in the last class. Yeah.
When we are going to use mean pooling, the slide says the gradient will be downscaled to 1/.
Yeah.
So can we say that smaller corner is better for mean pooling?
Smaller what?
Smaller corner size is better.
The smaller window? The kind of, it depends, right? Mean pooling is supposed to be smoothing out. Mean pooling is your alternative to max pooling. And basically, it's supposed to introduce some kind of jitter invariance. So how much jitter are you willing to tolerate? You generally don't make your pool, you don't perform pooling over very large windows, 2x2 or 3x3 is the largest you will go anyhow.
I think if we have large corner size, then the gradient will be vanished.
The gradient is, well, it won't necessarily vanish. Tell me why. Because if you take any particular element, as you keep stepping forward, that element is going to get derivative contributions from many steps going forward. So there will be no vanishing of gradients at all, as if you have a stride of 1, right? Anyway, we saw downsampling layers and upsampling layers. When we were downsampling, basically we had a map of this kind and we wanted to drop, say I was downsampling by a factor of 2. I wanted to drop every second element, right? So I'd be basically dropping every second column and every second row. And then the resulting things are going to be packed into a smaller group, right? Now, when I'm computing derivatives, do any of these elements, now, when we are computing derivatives, regardless of the operation, the size of the map, the size of the derivative is going to be the same as the size of the input transposed, right? Forget about the transposition, but the size of the derivative has to be the same as the size of the input itself. And so the size of the derivative of the loss. So here, the derivative of the loss with the divergence with respect to the output is going to be 3x3. But the derivative of the divergence with respect to the input would be 5x5. So 5x5 went in and contributed to the computation of a 3x3 output. So going backwards, the derivatives are going to keep modifying their size, and the derivative size of the derivative is always going to be the size of the input. The only question is, what are these values going to be? Now, again, go back and remember what a derivative means. A small perturbation of the input results in some perturbation of the output, and the ratio is the derivative, right? So here the output that we're speaking of is the loss. Now, will perturbing any of these guys, the ones that have been shaded out, contribute to the loss? So what are their derivatives going to be? Zero, right? What about this guy? Does perturbing it contribute to the loss? How does that correspond to the derivatives here? 1 to 1, right? So this guy is the same as this. Whatever perturbation this results in is going to be the same as this one. And so when I'm going backwards, firstly, the gradient of the divergence with respect to the variable will be the same size as the variable itself. Remember, I'm speaking of the gradient, which is the transpose of the derivative. And so for the input of a downsampling layer, the gradient is going to be the same size as the input itself. And specifically, when given the derivatives here, I need to be able to compute the derivatives out here. And using the simple rules that we just saw, here's what we will do. When I'm computing it, I'm going to allocate a derivative map the same size as the input itself. But for these elements which never contributed anything going forward, the derivative is obviously zero. I can just blindly fill them out to zero. For the rest, so those are zero, right? And for the rest, I can just copy the values from the output over. So the downsampling layer, the computation of derivatives for a downsampling layer is very trivial. What does this look like? It looks like upsampling going backwards, right? So now, you can't use your upsampling code necessarily to compute the derivatives for the downsampling operation because there may be a shift in the positions of the zeros. But the operation is basically one of upsampling, right? Now, so you just copy these things over. I have some pseudocode for it, but that's the idea, right? Now, what about the upsampling layer? What happens? In the upsampling layer, what we saw was that we introduced zeros. For some reason, my laptop is sending the wrong colors today. We introduced, those things are supposed to be black. Okay, we introduced zeros going forward. So if I wanted to upsample by a factor of 2, then I'm going to introduce one column of zeros between every 2 column of elements and one row of zeros between every 2 rows of elements, right? Now, when I'm going backwards, what is the size of the derivative here going to be? Somebody, pardon?
Same as in.
Same, no, out here at the output. What is the derivative size going to be? 5 cross 5, right? What is the derivative size going to be at the input? 3 cross 3. Now, will the derivatives at the elements which I have introduced be 0? Will they be 0? Stop and think about it. Why will they be 0?
Because you're just adding 0, like you're not.
But would perturbing that 0 a little bit change the output? Because they contribute to the loss, right? So just because you inserted zeros going forward doesn't mean that those zeros are meaningless. At those locations, you will still have derivatives, right? But then, yes.
But wouldn't the zero not be a variable? Wouldn't it be like a static?
It's, as far as a derivative is concerned, the derivative is simply answering the question. If I perturb this a little, will the output change? And by how much, right? So there would be a derivative, right? So at this location, you'll have derivatives for the entire thing. Is there anything in the input that I can perturb to change these guys? Those are just a static 0 elements that I stuck in, right? I didn't consider the input when I stuck in those zeros. What is the derivative of any of these guys that have been introduced with respect to any input element? 0, because they are not dependent on the input. Now, what about the remaining guys? What is the derivative over here going to be? What is the derivative at this 0, 0 location going to be? Anyone? Derivative with respect to the derivative of the divergence with respect to the element. That's going to be the same as, okay, can somebody just speak up aloud and tell me how do the derivatives here correspond to the ones here? They're the same, the ones, because over here I just copied this value over out here, correct? And so when I'm going backwards, these values are not functions of the input, they're just introduced as 0 regardless of the input. So their derivatives, they have no derivatives with respect to the input. They do not contribute anything to the derivative going backwards. But the rest of them, they have a one-to-one correspondence. They are the same value copied over, right? If I perturb this value by some epsilon, this guy too is going to be perturbed by the same epsilon, and that epsilon is going to affect the loss, right? And so I can just copy this value over. What does this operation look like? Downsampling. So the backward operation through an upsampling layer is going to look like downsampling, right? It's not exactly the downsampling simply because of the specific positions of the zeros, but conceptually it is downsampling, right? And so I have some pseudocode for it. Okay. Now, when you have convolution going forward, followed by a downsampling layer, typically you will perform convolution with a stride greater than 1, right? So if I'm saying I'm going to perform a convolution, then I'm going to downsample by 2, it means I'm going to perform a convolution, then I'm going to drop every second element. So instead of dropping every second element, computing every second element and then dropping it, which is, wasted computation, going forward, I can just stride forward by 2 when I perform my convolution. But then when I'm performing back propagation and computing derivatives, if you want to think of convolution with a stride of 2 and you try to work out the arithmetic, if you want to see what the correspondences are and try to figure out which things to add to compute the derivative at any location, that's going to give you head spins. Just trying to figure out the arithmetic, right? It's much more convenient to just think of it as convolution with stride 1 followed by downsampling. Because when I do that, I know exactly how to backpropagate derivatives through the downsampling, and I know how to backpropagate derivatives through the convolution. So I can chain them up. Making sense? Right? So simplify the operation. Don't try to do fancy math. Try to figure out, you could, and you probably will save a little bit in terms of computation, but it's probably not worth your time to figure this out because you're more likely to be introducing a bug than than saving computation. Computing a lot of rubbish really fast is not really helping you. The speed is irrelevant, right? You could have just replaced it with a random number generator and be done. So this is how we would actually want to do it. Now, same thing, if I'm convolving with a fractional stride, which is to say I'm upsampling, increasing the size of the map, here you would actually explicitly be performing the operation in this manner, upsampling by, and then performing a convolution, although there are ways of sort of combining the two to get something to be a little more efficient. But then whatever your efficient implementation is, it doesn't make sense to think about your operation in terms of this fancy convolution with fractional strides that's going to kill you during back propagation. And so the way you would want to think about it is that you upsample and then you follow it by convolution. Okay, makes sense to everybody? Okay. And so for backprop, now we'd actually backpropagate through convolution and then backpropagate through upsampling, both of which we know how to do because these are really simple operations. Questions, anyone? No. Okay. So, but then for pooling, what we usually do, pooling is not a very useful operation if you're going to be pooling with a stride of 1, because you're trying to introduce jitter invariance, and that means you're grouping these things and they're all contributing to one element. Having the same element contribute to many windows is probably not the most meaningful thing to be doing. So typically pooling is performed with a stride greater than 1. But then again, it's convenient to think, so you're going to be striding, let's say, in this case 2. But then again, it's kind of convenient again to think about it as writing all of your operations, whether it's back propagation through pooling or back propagation through convolution as performing it, what you would do with a stride of 1, because that is conceptually very simple. And so decomposing this operation, whenever you're performing an operation with a stride, it's sensible to decompose it into a chain of 2 operations, the basic operation itself, and then a downsampling. And then you'll perform your back propagation through the downsampling, and then through the pooling, right? So this is all very simple. But there's an even simpler and mechanical and brainless way of doing it. I don't mean it's unintelligent, I mean you don't have to think. And in fact, maybe this is more intelligent, right? The code is simpler. Why is that? Now, when I perform conventional convolution going forwards, I'm going to be scanning left to right, top to bottom. At each position, we scan through the output channels. And then for each output channel at each location, you're going to, at the location, you're computing the affine value, which is the sum of the product of the filter and the input at that location, right? And then finally, we apply an activation. So when we did a back propagation and we just modified this code, what did we do? Anyone remember? How did we modify the code? Someone at the back, can someone answer me? Nate, can you answer me? What did we do?
I'm not sure.
Somebody else? All we did was just reverse the order. This is back propagation, right? So all we did, literally all we had to do was to say, in each of these loops, I'm flipping the order of computation. So we went from, instead of going from 1 up to this value, went from that upper value down to 1. In every loop, we just reverse the order. And here the activation was applied at the end. So here, the first thing we did, because we're flipping the order, this was, y equals some f of x, f of z. So it's going to be dz equals dy times f prime. This is a simple rule that we saw, right? And then out here we had, we had z plus equals w times y. So the rule we applied was dw was dz times y, and dy was dz times w. This is a simple rule that we applied, right? And so that's that. It was a simple change of the code. You can literally inspect the code and you know how things change. And just by using these 2 simple rules, we were able to implement the back propagation. Now, when you look at it this way, then when you begin performing operations with a stride, it simplifies stuff. What do I need to do? Literally, the only thing that happens, the only difference between a regular forward convolution and a convolution with a stride is that you have a stride, right? When you're stepping forward, you're stepping forward more than 1 element at a time. So you're sleepy? You want to go out and wash your face or something? You fine? I know it's very early in the class, so it's okay. Try to be awake. So if I wanted to change this to perform back propagation, what would I do? Maybe you can tell me, Haditi. If I want to change this code to perform back propagation, what would I do? Switch no. Wait, somebody else? Chandra, you want to tell me? This is my forward code, right? I'm going to use the same logic as here. This is back prop. What would happen? Adnan?
You do the 1 to, instead of going 1 to n, you do n to 1 and
except all you would do is have a stride there as well, right? So all you need to do is now, you have to just go backwards. It's the exact same operation, except that you're going to reverse the order of all of the indices, and you're going to go backwards also with a stride, right? When you're going backwards with a stride, you have to do some extra work to maintain the appropriate indices. But other than that, this looks ugly, but all that really, the extra code, all this has to do with the indexing, and that's about it. But really, all you're really doing is just changing the order of the computation. The same computation that you had going forward, you'd flip it, right? you had to worry about indices going forward, you'd also have to worry about indices going back. That's all. That making sense? Right? So from the code, if you look at it with code, through code, it's easy. Similarly, if I were performing max pooling with a stride, then I'd be going forward with a stride, right? So when I'm going back, so when I'm going backwards, in fact, for max pooling, it looks even simpler. Consider this, at each location I'm taking a step forward, and then I'm storing the index of the location where the max came from, and I read the value of the max from this location, right? So going backwards, I can just go backwards through my pooled output. And at each position, I already know the index of the location of the max. I just copy the value over to the input derivative at that location. So the code is even simpler. And the same thing for mean. For mean pooling, you'd be going forward with a stride. When you're going backwards, again, all I do is flip the order of the computation and handle things. But anyway, so again, these pools are probably not going to be up. They're up now? Okay. Someone got scared. This is a simple poll, shouldn't take much time. So I'll give you 10 more seconds. All right, so guys on Zoom, I have nobody here to tell me your answers. So I'm going to ask you if, I'm going to ask you the answers and I'm going to have to hear your voice. Does someone on Zoom want to take the first question? What's the answer?
Is it true?
Someone on Zoom?
True.
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 There's no one on Zoom.
True.
True.
Yeah, 110. So why is nobody speaking up?
True.
They did? Well, okay. What is the answer? True. Okay. Someone here? What is the answer to the second one? And the third? Thank you. Right? Beautiful. So we've seen how we can compute the derivatives all the way going back through the network, right? Very easy. So if you actually break these things down, you can look at it at a code level, but even conceptually, procedurally, there is nothing particularly complicated. If you're wanting to compute derivative, through the final MLP, it was fairly straightforward. The computation was just what we did for MLPs. For the convolution layers, do you mind shutting your laptop? Yes, thank you. Right, so for the final convolution layers, if it was a regular convolution layer where you had to compute the derivatives for the input, all you did was, for any particular channel, you just pulled out the corresponding channels of all the filters, transposed those, and then convolve those with the zero-padded derivative map of the output channels. And to compute the derivative for any filter, you just convolved the output channel, the derivative map for the output channel with the input channel values itself, and you got the derivatives for the filter. So now, why all of this transposition, right? What you might have observed is that as you're going backwards, everything seems transposed with respect to what you did going forwards. What is the logic behind this transposition? In pretty much every single operation, you were considering the columns of the filter going back forward. You were considering the rows of the filter going backwards, right? You were considering the filters as is going forwards. Going backwards, you flip the filter both ways. So what is the reason behind, or the logic behind all of this transposition? The logic is very straightforward. And here's how you can think about it. This has to do with the fact that when you're going backwards, the derivative for the input has to, the gradient for the input has to be the size of the input, right? The gradient for the output has to be will be the size of the output. Now think of what happens when you're just computing the affine value, the linear layer. So let's say I have some linear layer, A wide, and let's say this is M times, M elements, and then the output over here is N elements. Then when I'm going forwards, I'm going to have W times, let me call this, Y1, and let me call this Y2. So Y2 is going to be W times Y1 plus a bias. Skip the bias for now. What is the size of W going to be over here? This has got to be N cross M, correct? Because you want the output to be size N and the input is size M. So this is going to be size M. This is going to be size N. So this has got to be N cross M, right? This is going forward. When you're going backward, what are we doing? When you're going backwards, we have the derivative for Y1. From this, we are computing the derivative for Y2, and you're multiplying it with something. What is the size of? Actually, you're going to have the derivative for Y2. From this, you're computing the derivative for Y1. What is the size of this guy? This is going to be the size N. This is going to be size M. What will this size be that you're multiplying it with? M cross N, right? So if you look at this term versus this term, this is the transpose of this. You see? So, which is why when you're going backwards, everything gets transposed. The sizes are in inverse order. That making sense? Logically. So this is something you want to keep in mind. If you're writing code, if you're working out the math, anything, if you think about the sizes, you know that going backwards is always the transposition of going forwards, right? So the story so far, the convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that can scan the outputs of the previous layer, and downsampling layers that operate over groups of outputs from the convolution layer to reduce the network size. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element in each pool. And other pooling operators use, gradients or subgradients. If your max requires subgradients, mean pooling requires gradients. Derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. So the derivative formulae end up looking more complicated than just a regular derivatives going for an MLP. And this has to do with the fact you might think of it as a consequence of convolution. You might think of it as a consequence of all of these fancy operations, but basically at the root of it, that is not the reason. The real reason is that it's a shared parameter network. Anytime you have a shared parameter network, you're going to have pooling of derivatives going backwards, summing of derivatives going backwards. Questions? Yes.
For CNN, the model is only effective for translation. How can we achieve many other transport invariants?
Okay. So now CNNs are position invariant. They are shift invariant, right? What about rotation, scale, or reflection invariance? How would we deal with it? So does anybody want to take a guess? How did I deal with position invariance when I was doing NCNNs? Scanning. I used the same filter and looked at it. I used one filter and I checked every location with that filter, right? If I want reflection, now remember, a filter is something that searches for patterns, right? If I also want reflection invariance, what would I do? What are you talking about? I'm not giving you the data or allowing you to augment the data. You'd have to increase the size of your network. I'm not talking about CNNs, right? Did I data augment when I wanted position invariance? No, right? So using the same logic, if I want to have reflection and variance, what would I do? I can flip the filters, right? So I would look for the filter pattern at each location, but I'm also going to look for the flipped pattern, right? If I want scaling and variance, what would I do? I'd scale my filter and look at each location. So I can get, if I think about shift and variance, basically what we have is a filter. You can think of it as a basic filter that's shifted to different locations where you're computing an inner product, right? If I want to make the operation also invariant to something like, say, rotation, I can take the same filter, but then rotate it a little bit and then check each position. If I want, reflection, I can reflect it a little bit and check each position. If I want an arbitrary transform, I can transform my filter and check each position. Now, these are not trivial operations because if I want to, I'd have to figure out this is a discrete grid, the filter. So how do you deal with transforms? How do you deal with reflections? How do you deal with rotations? These are things that, these are formulaic operations which must fill in the, which you require to actually compute what the filter would look like if it were rotated by, say, 10 degrees, right? But besides the fact is that if I want to scan for something if I want to say, I want to find this pattern regardless of whether it's this way or rotated by 45 degrees, I take the same filter pattern, scan for it, but then I rotate this filter pattern by 45 degrees and also scan for it. And so, if I have a set of transforms that I want to be tolerant to, then for each filter, you're going to make copies of the filter, which have been transformed in every one of these ways. And then you're going to scan the input with all of these transform versions. Now tell me, if I have a single filter in standard convolutions, how many output channels did I get? One per filter, right? When I transform it, how many will I get? One per transform per filter, right? So the number of channels is going to blow up. And so this is your standard convolution. This was your scanning left to right at each position. You're just moving your, here's my second shamefaced TA coming here. So, guys, I missed you. All right. What do I say? Anyway, so I'm shifting the filter to various locations and taking an inner product, as you can see, right? You can either think of saying I'm shifting the window that I'm looking at, or you can think of shifting the filter itself. Over here, what we would do is transmute for each filter, you're going to scan through all of the transforms as well. And then at each segment, you're going to transform the filter. And then you're going to compute the inner product. Now here, a rotation is an ugly operation. A reflection is an ugly operation. If I want a nonlinear distortion, it's an ugly operation still. But really, all of these transforms are just maps. You can store them as tables. If I have a 3x3 filter, there's some transform, and this results in a different 3x3 filter, right? So this is basically just a 9-element table, which tells me how the filter was transformed. So you can think of or a position or these 9-element table, for instance, if I were looking at reflections, I can say element 1 became element 7, element 2 became element 5, and I can just store this table in terms of computations. And so once you think of it this way, you can have all kinds of arbitrary transforms of your filters, right? The real trick is computing derivatives. All of these transformed versions of the filter must contribute derivatives to the same basic pattern. And that is a headache, because how do you transform these derivatives, pass the derivatives backwards through the transforms to give you the derivatives for the original filter? That's non-trivial. And so, you can maintain these tables and say this element here is the transform version of this element here, and then you know where to copy or sum the derivatives over. More generally, it's not going to be that simple, which is why you don't actually see a CNN code which uses transforms. There are two disadvantages. One, you can only enumerate so many transforms. You have to enumerate the transforms. You can't say, I'm looking at all kinds of scaling. You can say, I'm looking at a scaling by a factor of 2, by a factor of 4, by a factor of 0.5. It's not looking at everything, right? Secondly, the outputs are going to keep blowing up with, multiplicatively with the number of transforms that you have. And three, going backwards is a pain. The arithmetic can get arbitrarily complex. So what is the easier solution? Now you tell me. Data augmentation, thank you, right? So typically what we will do is not bother with this transform invariance. You just transform, just augment your data. Did that answer your question?
Yes. But I have thought that
Yes, what is the question?
it's not clear, so I cannot say that.
So where did I lose you?
Is it possible to just expand train convolution?
These are all convolutional networks. Everything is being trained the regular way, right?
I mean, for example, from
So I'm not clear, I understand. So take this offline. When you're not sure of the question and I'm not sure of the answer, piazza is here. Okay, so story so far. We just added this extra line to the story so far, which is to say the models can be easily modified to include invariance to other transforms besides shift. But this is not a convenient thing to be doing, so you probably won't do it. You won't see a lot of libraries doing this. Now, what about the exact location? We started off saying that we want to detect if this image has a flower. But sometimes you also want to ask, where is the flower, right? And that information is getting lost in all of this. If I also want to find out where the flower is, I need some extra process. I want to say, yes, this has a flower, and here are the 4 corners of the bounding box where the flower actually is present. And so for that, here's what we can do. For some reason, all of my colors are distorted today.
They said it was something with the projector that they're trying to fix.
Oh, I see. I thought it was my laptop.
It's fine up here.
Okay. It's easy for me to believe that my laptop is messed up. It's much easier for me to believe it's messed up than the system is messed up. But anyway, here's what we can do is we can actually add a second. When you flatten the final layer, right? We were just doing a max or some operation of that kind to figure out if a pattern existed, but we said we can also pass the whole thing through an MLP. Now, if I were to take flatten the final layer output and pass the entire thing through an MLP, does it remain position invariant? Anyone? Can you say that aloud? Yes or no? How many people think no? Raise your hands. And how many people think yes? And why do the rest of you not have an opinion? Right. So Aditi, you tell me, yes or no? Why not? Because the position is also encoded in the final output, right? The final layer outputs have their positions. If I'm not if I'm not sort of grouping the whole lot of them, but treating them as separate, then the final MLP might just key in on saying, I need to find something in the upper portion of this flattened vector or the lower portion of this flattened vector, and then you will end up with some level of position dependence. So this flattening and passing through an MLP loses some of the position invariance that we began with when we started considering convolutional networks. You can, yeah.
Moved ahead, but I had the doubt before during the transformation section. Can we not just do the filter transformations during test? If we do it during training, will the training be stable? Because we have this weird constraint that the parameters need to be shared and needs to be rotated.
Correct. So you could, I have not seen anybody try. That's a good idea. That's actually, you can test it. We have a volunteer. No. So here's the thing. The final layer outputs carry information about the position, right? So which means that I can actually analyze the final layer outputs with some additional processing to try to find the location of the input itself. And so a standard operation over here is to say, I'm going to add this extra second layer, which is predicting the corners of the bounding box, which can be provided as part of my training data. In my training data, I'll actually draw the bounding boxes. And then during test, I will try to predict it. You can define a union over intersection error, intersection over union error, or any other kind of error and try to minimize that loss as well. So yes.
Do we still have the position information even though we have a global average pooling something?
Once you do a global average pooling, you will not have it, right? Because that is gone, correct? Yeah.
So in the label, do we need to have the coordinates?
The coordinates of the four corners, right? So, and now you can actually predict it. And now you are minimizing two losses. One is the upper loss, which says is the pattern present. The lower loss says, where is it? And so this is a multitask learning framework. You have performing two tasks at the same time, detecting it and finding the position. And the same mechanism can be used to do the spooky business. I don't know, none of you have seen Yasser Sheikh's demo because it's been taken down. But if you were walking from Newell Simon, from Hillman towards Newell Simon, as you walk down the corridor, there was a big screen at the end. And as you walk down, it was very spooky. It would actually draw your skeleton. And it was precise. It was very precise. I mean, Yasser is a genius. He got this done. And it's live. You'd just be walking down and watching your skeleton walking at you. And so how do you do something of that kind? Your body is a bunch of joints. And so you can just predict the positions of all of these joints as a person is walking using the same technique. And you can make it arbitrarily precise, and now you can connect them up and you can spook people. So, or you could do this for pose estimation, for instance, right? Here's a pose. Okay, 10 seconds, guys. Shouldn't take that much time. You're tracking Zoom.
And we are leaving the polls until the end of the class. Right?
Yes. Okay. Does someone on Zoom want to take the first two questions?
That true.
What's the answer to question 1? True. Is there an answer on Zoom?
True.
Okay, and the second one? True. What about the third one? Right? Perfect. All three are true. So this was easy. Now, there are many variations, very deep networks, 100 or more layers in an MLP. This is a formalism called a ResNet. You'll see this in your homeworks. Depth-wise convolutions. Depth-wise convolutions are an interesting case because they take the shared parameter concept to the next level. So let's take a look at depth-wise convolutions. Now, when I'm performing a conventional convolution, here's what you do. You have a filter. The filter has many channels, right? The filter has as many channels as how many channels does the filter have? As the number of input channels, right? The real operation that's happening when you perform convolution is that each filter channel convolves with the corresponding input channel and produces an output affine channel, right? Then all of these are just added up. And that's going to give you a final affine map. This is the actual computation that's happening, regardless of how you implement it, right? You might be collapsing it point by point before going ahead, or you might be computing all of them and then collapsing it. But the actual operation is that every filter channel is convolving the corresponding channel of the input, and the entire thing is being added up. Now, if I have a whole bunch of filters, then every filter has its own collection of channels. So in order to compute any particular output channel, you're going to convolve every input channel with the corresponding channel of that filter. So you're going to get a bunch of output channels, and you're going to add the whole lot up to get the final output for that filter, right? So when you compute the output maps for the actual computation done is shown over here. You're going to be computing one channel per input channel per filter. And then you're adding them all up, right? Here's a different way of doing it. I can just have one filter with many channels. I keep the channels separate. And instead of computing these many channels, right, and then just collapsing them, I can compute just one set of channels and then sum them up with different weights. So every filter channel is going to, it's now I just have one filter. Every filter channel convolves the corresponding input channel. And so you're going to have this bank of first level bank of output channels. And then instead of just saying I'm summing them all, I can make it a weighted sum. And the different output channels are going to be different weighted sums of these guys. Making sense to you guys? I see a big question mark on your face. Okay. So did you get this? Okay. Instead of having these many filters with different colors, when you did this, for each filter, you just computed all of these channels and just summed them up with no weights, right? And I got as many output channels as filters. Now, for the depth-wise one, I'm going to have this one filter. I'm going to be convolving each channel of the filter with a corresponding input channel, but I won't collapse them immediately. I'll take a weighted sum. And if I change the weights, I will get different outputs, right? I'm still getting as many output channels as I want, but the total number of parameters is vastly reduced, right? More importantly, the total computation. Here, I had to perform, if I had k filters and I had n input channels, I had to perform k times n convolutions, right? I only perform n convolutions. There's a factor of k reduction and the number of convolutions I have to perform. So this, if you're running things on small devices, for instance, this would really save things, would save computation for you. And so to compare, in your conventional computation, each of these filters is going to compute as many output channels as the number of input channels, and then you collapse it. Whereas over here, you're going to have one filter which performs all of its convolutions, but the channel-wise outputs remain separated. And then over this bank, you're going to be collapsing them with different weights. But collapsing them with different weights is equivalent to saying I have this bank of channels and I'm scanning it because it's a point-by-point collapse, right? So I'm scanning it with a vector of weights. What is scanning with a vector of weights? Pardon me? But what kind of convolution? This was the non-distributed convolution, remember? Right. So basically, instead of having, you're eliminating the distributed portion of it. But this is a case where doing so in this manner actually reduces the number of computations. And so this has far here. Yes.
I guess the word depth-wise doesn't really make sense to me. I don't really know why that's depth-wise compared to the other. Is there?
The depth-wise is simply because you're keeping all the things separate. Don't ask me about terminology. I didn't create it. Right? I would call it channel-wise computation, convolution. But then someone called it depth-wise and the terminology is stuck, and there are people on the internet who will give me lessons on why it must be depth-wise. And maybe they're right. But you get the idea, yeah.
Are these two equivalent? Because
Are they equivalent?
like it doesn't look like they're equivalent because we're learning different for these.
If you have a different set of number of parameters, are you going to end up learning the same things? No. Yeah. So they're not going to give you exactly the same kinds of outputs, but still, it's still shift invariant pattern detection. Right? Here's the pole. Track it. Okay, 10 seconds, guys. Okay, so does someone on Zoom want to take the first question? Do we have an answer? False. Okay, let's check if that's false or not. And so Alex, what is the second answer here? True. Let's check. You're right, right? So filters do not convolve, do not sum the result, right? They keep them separate, as opposed to conventional filters where they sum the channels. And depth-wise convolutions require far fewer parameters and far fewer computational operations than regular convolutions. So continuing our story so far, CNNs, we saw a shift invariant neural network models for shift invariant pattern detection. The parameters can be learned through regular backpropagation. Like a regular NLP, individual layers may either increase or decrease the span of the representation learned by upsampling or downsampling. After all, what is upsampling or downsampling? That's increasing or decreasing the size of the representation. The models can be easily modified to include invariants to other transforms, but these are computationally and logically and procedurally painful. And they can make predictions related to position and arrangement of target objects through multitask learning. And last but not the least, there are variations that exist to obtain greater parameter efficiency, better ability to compute derivatives, and so on. Yeah, yes, Nate?
So we can code invariants to other types of transforms, but it becomes like combinationally like very, very large, right? If you're trying to encode all different sizes, all different
Yes.
permutations, right? And so we get around that by having a more robust training set
Exactly.
that then picks up. But then why not just do that like from the beginning for
Position invariance, right? Yes.
And also like presumably that is also combinationally large, where even if you have a huge training set, if there's a specific transform that's not in that training set, maybe you wouldn't learn that.
So we need a sweet spot somewhere,
Yep.
right? Anytime you want to, transforms are one variant of, a shift is one instance of a transform, but it's the most significant instance of the transform. So to try to collect a training data which goes over all possible transforms, that's possible or likely feasible for other transforms, because you're very rarely going to see human beings walking around upside down, right? But you do see them all over the room, right? So we have to pick and choose, and the position invariance is the obvious thing to go for.
Okay.
Right? So what do the filters learn? Now, speaking of humans walking upside down, have you guys heard of the experiment where someone actually wore prisms on their eye which turned the world upside down? I actually saw this guy. He'd be riding around MIT with these fat things. And then apparently one day he took them off, and then the world appeared upside down. Anyway, so what do these filters actually learn? You know that the filters in the lowest layers look for patterns which look like the arrangement of weights. But then as you go up through the filter, the next layer filter is looking for patterns, various patterns, over the lower layer filter outputs. So it's hard to predict what they look like. And then as you go further out, they become the patterns that these filters are searching for become increasingly complex, and it becomes increasingly difficult to predict what they're actually looking for. But these are the receptive field is the size of the region it's looking at, but it's also that we can also think of the pattern. What is the specific pattern that it's looking for? So what do they look like? Here, this was, here are some examples. They look spooky, but you can see that this was one way to figure out what the filter is looking for, right? Is to actually calculate it. The one thing you could do is to say, if this filter output is large, what does the input look like? And then you can compute that through regular backpropagation starting from some point, right? You can find out what triggered the filter, and you can do this for different inputs. And so here are some examples of a large image recognition neural network and its response to different kinds of inputs. So at the lowest level, you find that all of the neurons are looking for patterns of the kind shown over here. Do these remind you of something from our first CNN lecture, from our second CNN lecture? What are they?
In the S and the C cells.
They're not decision boundaries. They're like this. These are just like what the mammalian vision found. Oriented lines, right? So it turns out that when you learn these networks, the lowest layer network filters simply end up learning patterns very much like the very first S and C layers in the brain. So it gives us some confidence that these might be doing something very similar to what human perception itself does. But then as you go up, you can see how it composes the objects hierarchically. So when it's trying to recognize image faces, an intermediate layer actually detects parts of faces. So clearly it's first detecting various lines and such like, then it's composing those to create eyes, ears, noses, and then later layers compose them to detect different kinds of faces. Similarly, if you're looking at cars, this is not visible, you'll have to look at the slides, but the intermediate layers begin looking for detecting portions of cars, different components. And then the upper layers compose entire cars, yes.
How these images are created.
These are just the filter patterns directly, right? But then for any particular input, you can go out and check, okay, this neuron has a specific input, what happens? Which portion of the input gets really perturbed? How does the input really change if I perturb this? And so you can figure out what it responded to in terms of perturbations, right? So similarly, these guys were given pictures of elephants. It found portions of elephants and then different kinds of elephants, chairs. This is a failure of a slide, so I will move on, right? So when we train, you have all the standard convergence issues. ADAM or other momentum style algorithms are required. You need dropout, all of these things. You're going to encounter this in the homework. The number of parameters can quickly become very, very large. So you will get insufficient data to train well. You need data augmentation, which is to say that you're going to take your data and distort and transform them and add noise and make many copies of it to augment your data. This has two effects. One, of course, is it introduces robustness to a certain amount of noise and transform invariance, but then it also increases the size of your training data. So if you simply shifted objects around or scale them a teeny weeny bit, then no, shifting them around actually conforms to the original hypothesis of CNNs. But the other ones give you robustness to other things as well. Anyway, so CNNs are the most frequently used formalism today, used everywhere. They're used for not just for image classification, they're used for speech and audio processing. They use convolutional networks and spectrograms. They're used in text processing. You can just take sequences of words, vector representation of words, and run a CNN on it. And amazingly enough, the same concept seems to hold over there. So we started off with looking for position invariance. We sort of explained it to you saying this is how mammalian vision works. You develop a complicated model, and now you throw it at something completely unrelated and totally random, which has no relationship whatsoever to position invariance, and the whole thing still works. So at that point, it's hard to explain why they do what they do. But I don't know if Karpathi still has this demo at Stanford webpage. You should take it out to see what the network's like. But so let's look at some class of these success stories. CNNs were not always so popular. They've sort of taken off in recent years. And where does the story come from? The earliest version of a popular CNN goes back almost 30 years, more than 30 years, to Jan LeCun's LayNet, where he was trying to recognize handwritten digits. So this was his first convolutional neural network model. Now, before this, people were trying all kinds of simple classifiers, logistic regression, linear classifiers, other kinds of things to recognize these handwritten digits. And he showed that, firstly, you're going to have to scan for these digits. And so the real problem is not that, that classifying these digits is hard. It's that when someone gives you handwritten digits, you have to slice them out. And slicing is a very non-standard standard operation. You're going to have some shift. And while most machine learning techniques will give you perfectly reasonable results with these handwritten digits, if they're properly registered, shift invariance becomes a problem. CNNs actually in his demo, I think. We saw this demo a couple of classes ago. You could just scan the input and it would predict the output. So it did a very nice job. So what did this network look like? The inputs were 32 cross 32 handwritten digits. You had a first convolutional layer with 6 filters, each of 5 or 5 cross 5. And because they're 5 cross 5, they're going to lose 4 rows and 4 columns. So the outputs are all size 28 cross 28. And then he had a pooling of 2 cross 2. Again, when he was implementing this, he was just taking Fukushima's computational model of mammalian vision and adding supervision to it. But these were 2 cross 2. And so it's a stride of 2. So everything shrinks by a factor of 2. The 28 cross 28 becomes 14 cross 14. But then you're going to have 5 of those maps. He followed them up with 16 5 cross 5 filters in the second layer, which reduces the map size to 10 cross 10. And then a pooling layer with 2 cross 2 again. And then finally, he had an MLP with 3 layers. So it's a very simple model for the kind of results it got. Now, that's where things stayed for the longest time. For 20 years, CNNs were not really very popular until Hinton's team applied them to the ImageNet problem. Now, the ImageNet is a large-scale visual recognition challenge. It has a data set with many millions of images with thousands of categories. And the problem is to look at an image and detect which class of image, what the image actually has. So in this particular set, you have one evaluation, you had 1,000 categories, 1.2 million pictures, and the various categories are, mammal, placental. You can actually have this entire ontology of classes. It's a mammal, placental mammal, carnivore, it's canine, dog. But then there's a working dog and there's a husky, right? They're all different classes. A vehicle, craft, watercraft, sailing vehicle, vessel, sailboat, trimaran. So all of these are classes that you have in ImageNet, and you're supposed to recognize these guys. Now, people worked on this for several years, and the best classification performance error that anybody got was of the order of 25%. If you're looking at the top, so you have picking from 1,000 classes, you'd give an image and say, what is the class? And you say, is it in the top 5 selections? And if it is, then you say, then you call it a success, even if it was not in the first position. And even there, the best performance anybody got was like 25%, right? It's pretty poor. And then Hinton and co, Krzyzewski and co, really, published this paper in 2010, where they built a convolutional neural network with 60 million parameters. It was large for that time. It was so large that they had to distribute it over 2 GPUs. And because they distributed it over 2 GPUs, they had to draw a picture of the sky, which was too large for the paper they published it in, so the upper half got cut off. And so this picture has become very famous, including the cut off upper portion. And this is when they actually got, it's a lot of operations. They introduced a few things. They introduced, I think, ReLU activations in convolutional neural networks. Before that, most of the everybody was using sigmoids, and having a ReLU made the whole thing operational. They've added some things called normalization layers, which didn't really matter. And then finally, for testing, they would take the image and take different crops of it and test all of them. Each of them would give you a different result, and then you could take a vote. And when they were done, then there were a whole bunch of other tricks. So when they were done, the top 5 error went down from 25% to 18%. But moreover, when they actually looked at, trained 7 different networks and took a vote, that error went down to 15%. So you're looking like a 40% reduction in error on a task that everybody had been struggling with. And now suddenly everybody was using convolutional neural networks. So this was, the lowest prior error was greater than 25%. Now, these are some of the lowest layer filters that were learned. And again, you find that it's actually learning all of these oriented vertical and horizontal patterns.
What do they only use for in the four connected layers?
Their choice, right? I wouldn't know because things have changed, right? Because the performance has changed. But what they also found is that the network actually learned useful features. So here, for example, it's classifying a mite. You can see mite is in the first position, container ship, motor scooter, leopard. But even when it made errors, the errors were reasonable. So this is being labeled as a grill, and it comes in as a second position, but what's in the first position? Convertible. That's a perfectly reasonable prediction. The label is mushroom. That's in the second position. Here, the label is a cherry, but there is a dog in the background. So the first level, the first output was Dalmatian, which is completely, acceptable, right? Madagascar cat. It's really hard to identify. So squirrel monkey and spider monkey are perfectly reasonable. But even more importantly, they learned that, when you're performing the classification, you finally get a representation that's passed through your softmax. Those were meaningful. So they computed these features, the final layer representations for the entire data. And then they would take one particular picture and pull out all the other ones which were similar. So you were treating it as a retrieval problem. And so here, these are the queries and these are the responses. And you can see that when they give it a picture of a flower, the closest images are also those of flowers. For I don't even know what this animal is at this point, elephant, I think. All the closest ones were elephants. For a ship, all the closest ones were ships. Halloween's coming up, a Halloween pumpkin. All the closest ones were Halloween pumpkin. So the final level layer representations were also very meaningful. So it's learning useful things. And then, of course, things took off. We had Zeiler and Fergus in 2013, just a year later. They had the same architecture as AlexNet, except they increased the size of the filters and did a bunch of optimizations. The error went from 15.4 to 14.8%. They published it. Not a big drop, but still significant in the big scheme of things. Then these guys, they burned down half of the Amazon in running experiments. This entire table, right? And then finally came up with a network with 140 million parameters and reduced the error from 14.8% to 6.8%. Now you're looking at something that only a year and a half ago was at 25%, right? And then Google, of course, has to outdo everybody. So they came up with this that nobody can explain. But it's a convolutional network, that much. And they managed to bring it all the way down from 6.8 to 6.7. Right? Then, but the number of parameters was reduced from 140 million to 5 million. That's the big deal, right? And then, of course, ResNet, we were using it. You can train very deep networks with thousands of layers, and that error rate is like 3.5%. Again, consider that this is 2015. 5 years ago, the error rate was 25%. So you reduce it by 80% in 5 years. And details. Then someone came up with the dense net where you just, each layer looked at all of the outputs of all of the layers, all of the previous layers, and that error went down further. And the competition heated up. There would be daily updates. You'd go out for coffee and come back and the error would be down. So I stopped tracking these things. I don't put them up on my slides anymore. But anyway, you get the idea, right? ConNets really became, they were popularized by Hinton and his team with that AlexNet. That is the cusp of the curve. But now they're used everywhere. For example, in speech recognition, again, pretty much every system uses convolutional networks. If you're using things like there's even attention-based models use some convolution somewhere in between these days. So as a quick recap, using just on time, these convolutions are neural networks which have a specialized connectivity structure which include convolutions, nonlinearities, and pooling. They have supervised training. They're trained using backpropagation. They have models that, they have all kinds of stories tied to them, but the basic idea is position or more generally transform invariance through parameter sharing. But the idea is still that you're scanning with an MLP with different degrees of parameter sharing. This is the last of the CNN lectures. We'll stop here. From the next week on, we'll be talking about recurrent neural networks. If you have any questions, post on Piazza. Thank you.